Thank you, everybody, for joining us. Welcome to the NSERC PermafrostNet seminar series. We're very, very lucky to have Hosein Fereydooni presenting today after his packed room at the Arctic Change Conference. We're going to hear all about ground ice detection with spectral induced polarization. My name is Tristan McLean. I'm the Director of Operations for NSERC PermafrostNet. I'll give a little introduction about Hosein, and then I'll hand it over to him so he can present his seminar. So Hosein has had a varied academic career, starting with nuclear magnetic resonance in his bachelor studies and ground-penetrating radar in his master's. As a research assistant, he focused on integrating EM geophysics with geological and satellite data for mineral exploration. Further expanding his expertise, Hosein joined as a visiting student to Memorial University, where he conducted research on the inversion of helicopter time domain EM data. He is currently a PhD candidate in Earth Sciences at Carleton University, specializing in near-surface geophysics. His PhD research focuses on identifying ground ice in permafrost using spectral induced polarization and examining its dielectric properties. So I'll now hand over to Hosein to tell you all about his research.
Thank you, Tristan, for the introduction. Hello, everyone, and thank you for being here for today's presentation. For today's presentation, I will just go for a little bit introduction for spectral induced polarization. And after that, I will bring one field measurement that is done in Whitehorse in 2023 on a Pingu site. So for getting some introduction about spectral induced polarization, I want to start the background with some definition of the electrical resistivity tomography. In electrical resistivity tomography, most of geophysics know that we send some DC current to the ground. And at the same time, we have some electrodes that measure the difference voltage between these two current electrodes. And simply by using Ohm's law, we can calculate the resistivity of any material. And after, by using some geometric factor, like what you can see here, it just depends on the array of the different electrodes. We can convert those resistivity to apparent resistivity that the dimension just change from ohms to ohm meters. So by knowing that the ERT or electrical resistivity tomography using the DC source current, and it just measured the resistivity of the material. But if we are using the AC source current, then if we put a pure resistor, as you can see here, then by measuring the voltage and the current, you can see there is no phase lag between the voltage and current. So when we have a pure resistor, the difference and the phase lag between the voltage and current is like zero. So for two kind of measurement, first for the DC or constant current, and for the pure resistor, we don't have any phase lag between voltage and current. By that, we are going for some capacitor like what you can see on the right. So when we have a capacitor and when we apply an AC electrical field on that, we can see there is some difference between current and the voltage. Then we can call it the phase lag. For a pure capacitor, the phase lag between the current and the voltage is around 90 degrees. So for the real world, we have some combination of the resistor and capacitors. To introduce and know more about the properties of a combination of resistor and capacitance or capacitors, we have some definition by electrical impedance. By electrical impedance, we can introduce the real part. That means it's just being like resistor, and the imaginary part that is just being like reactance or capacitors. So by having the real and the imaginary part of a circuit or a material, we can introduce electrical impedance for those material. For each of those pair of real and imaginary part, we can translate and calculate the phase angle, the difference between real and the imaginary part, and we can calculate the impedance magnitude. By having the impedance or electrical impedance for one frequency, if we make a measurement through a spectral frequency, from the frequency near to zero to frequency near to infinite, then all of those things together, a spectra can be defined as a spectral induced polarization. So by measuring impedance in different frequency, we have SIP or a spectral induced polarization. And by having the phase angle and the impedance or SIP magnitude at each of these frequency, we can calculate the imaginary part and the real part. But why it's important for us? Because when we consider something like ice, when we put an external electrical field on those ice material, then the ice material just turned as dielectric materials. When we have dielectric materials, it can save energy on that. When we are saying that we just introduce ice as some impedance and have some impedance features. So SIP can measure the resistant and imaginary part of some ice. So what happened when we put some external electrical field on a block of ice? As you can see here, the external electrical field trying to relocate the direction of the current within the ice. In some frequency and some specific and unique time, ice and water molecules within the ice start changing the direction. And at some specific time, the direction of ice just being aligned with the direction of external electrical field. This phenomena just being defining by the polarization. And for this study, we just measured some polarization in low frequency. At that low frequency, we have some dipolar polarization and interfacial polarization. So by knowing the relaxation time, we can just have some better clue of ice. And it's a unique feature for ice because ice relaxation time just happen in certain time and unique time. As you can see here is a curve for water, and that one is for ice. And you can see in the imaginary part of the dielectric or SIP have some peak at lower frequency, or we can just translate the frequency to time, and we can say in some specific and unique time or relaxation time, we can identify and recognize ice from the other materials. But how we can get some of those value for the relaxation time? We have such thing like this equation. We call it Cole equation, and you can extract the relaxation time from this equation. So by having the relaxation time, we can get some clue of ice and identify ice from other material. By knowing of some background on the spectral induced polarization and the relaxation time, I want to just bring one example that we did in 2023 on the Pingo side. But before going for that, we know that most of part of Northwest Territory and Whitehorse, most of north, like west of Canada, just being covered by permafrost, some continuous and other part of permafrost. So changing in permafrost, I mean, aggradation and degradation can have some consequences on those areas. And the ground ice is a really must and important part of permafrost, because by melting the ground ice, then we have some degradation and some economic and other impact on those specific area. So here you can see some melting of the ground ice impact on Carmack's bypass. And there are some starting cracks on the road, and there is some ground ice melting that shows that underneath the road we have ground ice, and it start melting and make some problem. But a usual and common way to just recognize and identify ice is using ERT. As I told you, it's really simple. The ERT just measures the resistivity of the ground. And by knowing that the resistivity of the ground ice is higher than the other materials, we can recognize that some part of, for example, underground should be ice or should be just melted or it's just start sowing. For example, you can see we have higher value for the resistivity, and it shows that we have something like ground ice here, and the value of the resistivity just getting to lower value, and it shows that it starts sowing or melting. But it's not the whole story. The whole story is that it's true the difference between the resistivity of ground ice and other material is being a real big difference, but in somehow there is some overlap between frozen material and bedrock. For example, if in any area we have a combination of granite and ground ice, then just making clear which one is really hard because there is overlap between their resistivity. And at the same time, so some material like clay has a lower resistivity, and when they just being frozen, the resistivity of them not getting too much as like a frozen sediment. So at some time, maybe a frozen clay misunderstanding as not frozen by the ERT, and at the same time, maybe something like granite just misunderstood as ground ice by using ERT. For solving those things, we are using SIP because SIP just take a look on relaxation time, not just only on the resistivity. So for doing the measurement, we use the FOSS instrument. It just have a current unit and a potential unit. We send AC current by using the current unit, and at the same time we measure the voltage by using the potential unit. So what this device just measured, the device just measured the impedance magnitude and the phase angle. By using the SIP magnitude, we have these values, and by measuring the phase angle, we have the theta. So it's what we see on the laptop and the interface of the measuring of the SIP. We have the phase angle. At the same time, we can see the resistivity in ohm meters and the phase angle. And actually, we can just put some voltage. The voltage should be between 0 and 400 voltage. At the same time, the current should be between 1 and 1500 milliamp. So for the field measurement, we use FOSS instrument. The frequency coverage is between 1 millihertz and 40 kilohertz, and we measure 20 frequency. So before going for the field measurement, we need to just make sure that what relaxation time is related to ground ice. Instead of just using Cole equation, we use Cole equation because there is some probability to mix something else with ice. So we extract two relaxation time. And by other research and what we did in the field, we just run some short field measurement at the head wall of Soa slump that was just full of ground ice. And you can see here on the bottom on the right, some phase angle of those material. And finally, we conclude that the relaxation time on the field measurement should be between 10 and 400 microsecond. So it's the key for us, the relaxation time between 10 and 400. So we made some measurement in 2023 and 2024, like 6 site measurement. But today I'm just going for Pingo site in Haynes Junction. So it's a field that we measure in 2023. You can see it's like a Pingo site, and we have a profile length around 30 meters. And we had 2 potential units and 1 reference unit just for reduction of local noise. And we have other instrument and just doing the measurement by putting different electrodes and just changing the current and the voltage and just measuring the difference of the voltage. And finally, we measured around 600 SIP spectra over 20 frequency between 1 to 40 kilohertz over the Pingu side. So before going for the result and the method that we are presenting result should be resistivity. We somehow conclude that the real part data for 1 hertz should be like resistivity, because at that point we don't have any phase angle, and the phase angle should be near to 0. So we imagine that the real part at 1.46 hertz data should be like resistivity, and we have imaginary part at 40 kilohertz. And the imaginary part is important for us because imaginary part showing the capability of the material to save the energy that happens like the dielectric material in ice. And we have some equation like RFE or resistivity frequency effect. When it's just getting near to 1, it means that it has a more strong signal from ice, and it's just defined by this equation. And finally, we have the relaxation time or apparent relaxation time result for presenting the result of this field measurement. So before that, we did some pre-processing on the data on this field measurement. We exclude the negative resistivity values and the positive phase angle because it doesn't make sense to have something like negative resistivity and positive phase angle. And you can see here that a spectral ratio, for example, at 1 hertz, we just retain 65% of data, and for 40 kilohertz, we just have 95% of data after excluding those criteria. And I need to mention that there is some outlier here. I didn't go for extract the outlier for this presentation because of some reason. And you can see the result for different frequency. It just makes sense because the mean at like 1 hertz is a little bit higher than 40 kilohertz, and we have different distribution of the data at different frequency. So as I mentioned, the imaginary part is important for us. You can see the imaginary part result here. The imaginary part showing that there is some higher values and some anomaly here, that's showing that in the field measurement, we have some capability that store the external electrical field. At the same time, the resistivity results showing almost all the data at 1.46 hertz near to 0. But when we compare the result, I mean the imaginary part at 40 kilohertz and the imaginary part at 1 hertz or resistivity data, most of data showing like anomaly and higher value for the 40 kilohertz. And at the same time, we don't have too much values for 1.41 hertz. It shows that most of material here showing something like ice because they could save the energy. At the same time, we have some RFE result for the field measurement, and RFE showing some values greater than 0 and mostly around 0.2 or 20%. That's showing some kind of a strong signal for ice. So if we are going for just demonstrate what happened in the field, here is the apparent resistivity result in solar depths. So you can see the resistivity showing that in some area, maybe greater than 400 ohm meters, we have ice, but most of area and most of data point just getting just under the threshold of the resistivity. So we can conclude that the resistivity cannot show really a good result for this field measurement because having 400 ohm meter is really low for ground ice, and the ground ice should show like the resistivity more than 1 kilo ohm meters. But at the same time, the imaginary part showing that some signals of anomaly here, and you can see most of pixel have showing some strong signal of ice because we have something like greater than 150, and some values greater than 130 should be identified as ice. But these two results get some clue what happened in the field. But the relaxation time have different story. As you can see here, the relaxation time in this study area showing most of pixel and most of data relaxation time is near to 26 microsecond. And there is some point that that not being in the relaxation time of ice. And if we, because the relaxation time just related to some how to the temperature of the ground ice, by the other study and the lab measurement, we can say have some guess of the temperature, and around 25 and 26 microsecond, the temperature of the ground ice in this field measurement should be around -5, but it's not accurate. It's just some example. But we can see that the relaxation time result for this field measurement showing the strong signal that just comes from ground ice. But at the same time, on the field, we have a borehole near 22nd electrodes, 22 meters. And so when we take a look on the data at the location of the borehole, we can see that it's really matched with borehole log. For example, we have had some sign of ice from 10 to 40 microsecond for all of the area. But for the first part of that, we have the relaxation time showing a really large values that not belong to ground ice. At the same time, if we just consider apparent resistivity for the borehole, we can see that most of those data just being below the 400 ohm meters and hasn't had the ability to show any signal of ground ice on the borehole. And here we compare the relaxation at pseudo depths with the inversion for the imaginary part at 40 kilohertz and the RFE result. We know that the imaginary part and RFE has a really good result, better than ERT, but we wanted to just compare the relaxation time result with imaginary part at 40 kilohertz and RFE. And you can see there's a really good argument between them, but we can see the relaxation time. On the background, you can see the inversion result for the imaginary part and the data point showing the result for the relaxation. Most of pixels just have a good argument, but it shows that the relaxation time had the better ability to detect ground ice. It just happened like the same for the RFE. And we can see there is some agreement between those two data, but again, the relaxation time method could detect better ground ice than RFE. But because those data just compare the inversion result and the data result, we are compare those two with the data, not the inversion result. And here the imaginary part histogram, as you can see here, and we just choose more than 2 times greater than a standard deviation as anomaly, and then compare the relaxation time and the imaginary part. So we put the threshold between 10 and 400 for being ice for the relaxation time, and put around like 100 as being ground ice in imaginary part threshold. The results showing that so both criteria, I mean imaginary part and the relaxation time just being in agreement in 8% is not too much, and the imaginary part only could just detect ice less than 1%. And at the same time, the relaxation time, just by the relaxation time, we could detect more than 80% of ground ice, and around 9% or 8% of the data not being iced by two methods. And finally, we just compare the result with RFE2. For the RFE, we choose having just more than 103, no, just having around 0.2 as anomaly, as you can see here. And again, we have between 10 and 400 threshold for relaxation time. But at this time, the results showing better agreement, because right now we have around 30% agreement between the RFE and the relaxation time result. But same, most of pixel and data just being recognized as ice by the criteria that we introduced as ground ice by only the relaxation time. And at the same time, just being around 1% of data just being recognized as ground ice by just using RFE. And that's why, because RFE just take a look on two frequency, the lowest frequency and the highest frequency. But at the same time, relaxation time, just take a look on the whole spectra and consider every single frequency on the result. For example, if you have some clay material, RFE should not just get a really good outcome and result for those material. So by having that, I complete my presentation. And for the conclusion, because I'm just speak a lot about SIP and ERT, but based on what you are doing, maybe SIP or maybe in some cases ERT is just being really better method for identify ice. But for general, if you have a simple geological setting, it's better to use ERT. And if you have such thing like frozen clay, it's better to use SIP. And we don't have a really good development in inversion tools for SIP, no. So if you really want to have an inversion result, it's better to use ERT. And so we don't have like lots of equipment for SIP. At the same time, the capability of the detecting of ground ice content should be in SIP. And there is different criteria based on what we are looking on the field measurement and the situation. Either of those should be the best method for identify ground ice. And finally, I want to just thank from Yukon Geological Survey and Derek Moya, Patrick, Gabriel, Victor, and Panya and Olina to help me to just run this field measurement. And thanks for PermafrostNet for funding and Yukon Geological Survey. And yeah, it's my presentation. Thank you.
Fantastic presentation, Hosein. Thank you very much. We have some time to open the floor up to questions.
Hi, Hosein.
Oh, hey, John. Good to see
Yeah,
you.
very nice presentation. Thanks for that. Super interesting stuff. So I just I sort of just have a high level question. I mean, you showed some of the trade-offs that go on in resistivity properties of rocks, various soils, and compared to ice and whatnot, and that there's a lot of overlap. Those are based on lab measurements usually, right? Like if you put a rock sample into some lab apparatus and measure these sort of in the laboratory. Do you have that for relaxation time, like, or dielectric properties of various soils and those kind of things? I mean, maybe I missed it and you've shown it, but I was just wondering how they compare, sort of how distinct it really is in terms of relaxation time for ice being sort of 20 to 400 microseconds or whatever you said.
Yeah, we choose between 10 and 400. Before going for the field measurement, we made some measurement in the lab, but there is some problem in the lab because we have some surface conductivity in the lab measurement, and somehow there is some, just shifting for relaxation time and make some problem. But beyond that, there is some other study that just run the relaxation time for different materials. And we just use those published data. And actually, after that, by having, some signals of what would be the signal and the impedance and the SIP result for the ice, we went to the field measurement and just make some field measurement. And then by having the Cole equation, we extract the relaxation time in the field measurement. But to answer that, I can say that we just use other research data for the relaxation time and using the field measurement, our data for that, and just combine those together to get to a conclusion of those thresholds. Yeah.
So you think there would be like an advantage, say, in jointly analyzing resistivity and SIP data to sort of, I mean, you have this table in the end, but it seems like you can combine these things if you wanted to, right?
Yeah, I didn't quite get your question. You mean just integration between what? Between resistivity and relaxation time?
Like yeah, joint inference essentially. I mean,
Yeah.
you could like employ a rock physics model, say, or a rock soil physics model to kind of constrain these things, right?
I got your question, but because at the same time in the lower frequency, actually the SIP covered the resistivity data too. For example, if we just do a measurement at 1 millihertz, then the data should be the resistivity data. So at the same time, by just doing the SIP measurement, we have the both data, just having ERT data and SIP data. So I think we don't need to just go for different and separate ERT data, but we can just make some integration with other geophysical methods like near surface seismic and other things like, IP maybe. But honestly, IP have the same result for some specific frequency, but we can just take a look on other geophysical method for doing some integration between them. Yeah.
Thank you.
Igor, do you want to go ahead?
Thank you very much, Hosein, for this clear explanation of the complex geophysical processes of variations. And my question is regarding to monitoring and repetitive measuring this relaxation time of the active layer. So can we use this to monitor or to observe some ice creation during this frost heave, for example, ice lenses creation? Or can we do it continuous monitoring, or we can do this repetitive measurements?
Yeah, thank you, Igor. It's really good question because we are just started and this knowledge just being started. There is not really big development in equipment for having continuous measurement like ERT that just doing right now. But for the possibility, it's possible. But right now, because we are at the first steps, it should be really hard.
Yeah, I understand. Yeah, understand.
Yeah.
And also the soil classification may be a different soils can difference relaxation time in terms of frost susceptibility. Maybe we can just classify soil on these physical parameters maybe as well, because the soil particle size and the relationship between particles maybe affect this phenomena.
Yeah, so at this presentation, I just focused on the relaxation time, but there's lots of more data that we can extract from SIP data. But for the relaxation time, I can say two things can change the relaxation time. One of them is impurity. For example, having chloride just presenting in ice can just make some shift in the relaxation time, and temperature. But it's just somehow is a unique feature for ground ice and other materials. For example, other materials, other soil showing different relaxation time values, and it just being a unique properties.
Thank you.
Thank you for your question.
Once again, thank you very much, Hosein. Great presentation. And I think we're all looking forward to what this technique's going to be able to do in the future. So thank you very much.
Yeah, thanks for having me, and thanks for all the presenting. Yeah, thank you.